Okay, so we're almost ready for the next talk.
Until 11:45? 11:45.
Yes, I mean, if you were starting a little bit late, so if you
I think I'll be okay.
Okay, so let's start. So next, we're very pleased to have Elad Hazan as our next speaker from Princeton, and he will talk about spectral state space models.
Thank you, Bartolomeo. Thank you to the organizers. It's really fun to be here. Actually, I teach in this classroom sometimes, so it's nice to say something a bit more advanced to an audience. My name is Elad Hazan, and I'll talk about work with Naman, Shim'i, and Daniel, and recent work with Evan, Isabel, and Windsor, who are here. They're undergrads at Princeton. So I think everyone, by the way, you can hear my mic. Is this okay in the back? Yeah? All right. And another thing is I'm happy to take questions during the talk. It's perfectly fine. The most recent architecture that's been used in large language models, I'm sure everyone has heard about, is called transformers. And they're responsible for ChatGPT and many of the other large language models, which maybe many of you have used and definitely heard about. And these neural architectures have a computational issue, which basically amounts to the main component there is called an attention head. And the compute there scales quadratically with the context length, with how many words you apply the attention to. So if you're familiar with what I said, that's great. But if not, so I thought it's better to ask ChatGPT to explain this. So I asked him yesterday. Can you please tell me, I'm always very polite. My children ask me to be polite to the LLM. Can you please tell me what is the main computational bottleneck in the transformer neural architecture? And it goes to explain time complexity scales quadratically and so on. It does a fantastic job. You can try it. It also goes on and on about mitigation schemes and so on. So this is the motivation for a lot of work, actually, for this talk and a lot of other work. And starting from around 4 years ago, well, even before that. So recurrent neural networks have a history going back decades. The advantage of RNNs is that they are very efficient. They don't have this quadratic time blow up in the history. In fact, they are constant time because whatever the network size, that's how much time it takes to do one type of iteration and get the output. But they are unstable, so training them is very hard because of the inner connections. There are problems. Those of you who train neural networks using gradient methods know that there are problems such as exploding gradient or vanishing gradient. And these are well-known issues in training neural networks. The most common of these is LSTM. It has been surpassed by transformers in recent years. So around 4 years ago, there was a significant advancement. This is from the group of Chris Ray in Stanford, and in a sequence of papers, they revisited recurrent neural networks under a different name of state space models, but it's the same thing. The main advancement, or the main new component that they advocated for is actually getting rid of all nonlinearities, or vast majority of them. So they look at a linear dynamical system, actually with a diagonal matrix, which if you have complex numbers, it's without also generality. But they look at linear dynamical systems and architectures based upon them, again with the motivation of resolving this computational issue. And these have been exploding in recent years. Those of you who have been following the literature on recurrent neural networks have heard about the name Mamba and Samba, and every few days there's another architecture coming up. The initial paper is called Hippo, and I'm going to describe a little bit of what it does. But in general, these architectures have the advantage that they are much more efficient. They can revisit recurrent neural nets for sequence prediction, and they do it very efficiently. And they kind of resolve a lot of the issues of transformers. The downside is that they don't scale well in terms of context length, not for the computational issue, but for memory. So they don't scale well in terms of like remembering long context, and that is an issue in the example that I showed. You really do want the language model to remember history and understand what you're asking it, especially for a long dialogue. So there is a memory issue, and that's what my talk will be about. So the question that we're asking is, can we have something provable? And the provable comes because we went back to linear dynamical systems, so actually we can hope to prove things. There's a long history of proving things for linear dynamical systems, going back to Kalman and even earlier. And I would like to have provable long context, and I would like to do it in linear time. So that's kind of the wish list, or what we would like to consider in this talk. So I want to talk a little bit about learning linear dynamical systems, and then explain the main technique, which is called spectral filtering, and how it gives rise to a neural architecture, and finally talk about some experimentation. And let me start with linear dynamical systems. I'm happy that Sarah already talked about it a little bit. So I'm using exactly the same notation. It took me a while to kind of borrow this from the control people, but I got used to it. So we have a linear dynamical system described by the following equations. This is exactly the same notation as in the previous talk. We have an input series U and an output series Y. When we apply it to learning, to sequence prediction, to large language models, then the U's and the Y's are from the same family of objects. They are tokens from a language, they are words. And we like to predict, and what ChatGPT does, it does autoregressive generation. I'm not going to go into all of these details, but if you have questions, ask me. I'm kind of a bit familiar with it. So the way that a signal is generated, that the output is generated, is by these linear equations. We have an output that's a projection of a hidden state. This hidden state can have a very large dimension. And the hidden state is manipulated by a matrix A. This is the main object, the main system matrix here, because it keeps on multiplying again and again and again. That's how the past is incorporated into the future prediction. And we also have the input is also incorporated into the equations for both the state and the output. So this is a linear dynamical system. Everyone has seen this, right? Yeah? This is an audience, I think, that's very familiar with this concept. Okay, so it came from the study of dynamical systems. These are two examples that are one is very commonly given, the inverted pendulum. This is a setup in my lab that we studied during COVID. It's a dynamical system for ventilation, medical ventilation of patients that are sick. It's a one-dimensional input-output, but the reason I like to depict it is because the dynamics is very complicated. It's a human lung inside there, and you're kind of measuring the pressure, and you want to input air to make sure the patient is breathing well. And where does this come from? So this comes from a theory of control, where we want to control these dynamical systems. The formulation is very similar to before, but there are two differences. We have a state, we have an input. Now the input is something that we govern. So unlike the previous talk, but like generation, for example, we can control the input, we can select the use, and we also suffer a cost every iteration. And we might have some nonlinear dynamics. It was asked already today, what do we do with the nonlinear dynamics? And what Lyapunov said is that if the dynamics are smooth, we can linearize it. So almost without loss of generality, if you consider changing linear dynamical system, we can at every little time step linearize the nonlinear dynamics by taking the Jacobian. Okay, so this is all very standard. In this talk, I'm not going to choose the controls. It's all about prediction. I see the U's and I want to predict the Y's. And I want to do it, as I said, efficiently, and I want to also make sure that we have a large memory. So what does it mean? Here's the formal setup of what it means to learn a linear dynamical setting, and I'm using slightly non-standard now to control theorists because I'm considering of doing it online. But this is what actually happens in practice. You generate or you learn one word at a time, and you want to predict it. You don't know everything in advance. Okay, you cannot see it. You can train the machine, but if you want to predict, you do it one word at a time. So the way to formalize it is as follows. We have discrete time, and at every iteration, we observe the input U, and we want to predict a Y. and then we suffer a loss, which is, let's say, mean square error between the prediction and the true observation. Okay, so this is a setup of online learning. How do we measure performance? This is, again, used to be non-standard. Now the control literature is seeing more and more of that. So I like to measure when online learning, it is standard, by regret, which means the mean square error of the predictions of our algorithm compared to the mean square error of the best linear dynamical system that could have matched the data in hindsight. Okay, so this is a meaningful performance metric, even if the data did not come from linear dynamical system. For example, because it comes from the internet and there is no linear dynamical system, it's words that we wrote down in the internet. Okay, so this is still meaningful. Yeah, Amirali?
In the second bullet, yt cannot depend on past yt minus 1, or is that without generality?
Oh, our prediction?
Yeah.
Can depend on everything you've seen so far, yeah.
So not just the inputs.
Could depend, yeah, or could also depend on the previous observations, yeah. In fact, in Kalman filtering, other techniques, it does depend. That's when you have feedback loop, yeah, absolutely. Yeah, question?
One of the other key properties of a dynamic system, in addition to whether it's an infinite impulse response or finite, which is the part about depending on t minus 1, there's also a notion of a delay, and the fact that you have a d term means that the input immediately affects the output.
Right.
So a big discussion that has gone on in controls for a very long time in discrete time is when you have a lag, when you have a delay. So I was just curious whether your procedure can that accommodate those as well, because the whole point here is the current output is affected by something that happened.
Yeah. No, I'm definitely going to talk about historical, huge delay. That's the point of this technique.
Okay, very good, thank you.
Okay. Okay, so what do we do? How can we predict as good as the best linear dynamical system? The natural thing to do maybe is to identify. How about to identify the system? This is what Sarah talked about. We can look at the inputs and the outputs and try to use the Kalman-Ho algorithm or whatever to identify the ABC. It's of course a non-convex problem, but still if you have Gaussian, zero mean noise, even gradient descent works. This is work from 2016 by Hart, Recht, and Ma. So there are simple methods that can converge to the ABC, but in general, it's actually not true. In general, this is a non-convex optimization problem. So it's a hard one. What can we do? Well, here is a simple thing we can do. It's not what I will do, but it's something we can do. This is classic in optimization, so convex relaxation. We can forget about the structure of the ABC. I guess Sarah called it the Markov operator. So we can forget about the structure of the ABC and replace them by other matrices M and go back into the past a long, long while and kind of compute a Markov operator, learn a Markov operator by regression from the past to the future. Now, if you have followed or if you have looked at books in linear control, you will see that many times it is assumed the system is stable or strictly stable or various assumptions like that. This means that the spectral radius of the operator A is bounded from above by 1 minus delta, where delta is strictly bigger than 0. If it is bigger than 1, the whole thing explodes, right? So you have to be less than or equal to 1. And many times we assume less than 1, because then we can say, okay, how many terms do we need here? The effective decay of the system, it decays geometrically, 1 minus delta to the power, and we need something like 1 over delta terms here for the Markov operator to be precise, from the past to the future. Yeah, everyone has seen this, I hope. So, as delta goes to 0, this is problematic, because we basically need infinite memory. Okay, that's kind of the issue that I want to tackle. Even though this gives rise to an efficient algorithm, it's all convex and nice, the delta going to 0 is an issue. And that's the question I want to address. Can we learn, when delta is 0, we call it a marginal stable system. Can we learn it efficiently? So this is the technique called spectral filtering. focuses on this question. And here is a theorem that I will kind of sketch the proof of. Actually, we can. So for certain types of linear dynamical systems, I'm only going to address a small subset here, but the technique can apply more generally. So suppose that the matrix A is symmetric or positive definite. Even if the spectrum is equal to 1, we have an efficient algorithm that can match the best linear dynamical system extremely well. So exponential in the number of some parameter k, that's the number of filters that we're going to have, and independent on the spectral radius or how close we are to being marginally stable. Okay? So maybe if there is a question about what I want to show, that's a good time. Otherwise, I will show it. Okay, but it's clear why this is interesting, right? Because we can learn, well, delta is 0. We can still learn. It can go infinitely way back, and we can still learn it. Yeah? Okay. So how can we do it? And let me describe the technique for the simplest setting where we have scalar input and scalar output. The reason I want to describe that, because then, well, it's much less messy, and also the general case somehow reduces to it. We can diagonalize the matrix A and then learn each component separately. So in one dimension, up to constants, multiplying the whole equation, what we have is that the output of a linear dynamical system in the noise-free or zero-mean situation is given by the past u and then A times the u before it and A squared times the 2 before it and so on. Because it kind of recurses, right? This is when I unroll the equations of the dynamics. And I like to write it in vector notation in the following way. I have this van der Monde vector, 1, A squared, and so on. By the way, I assume I only go back L. L is the sequence length, multiplying the past L inputs. Okay? So this is what happens at time L plus 1, for example. So what I want to do is I want to consider all the vectors that are called mu A, and there are all these vectors that have a parameter A between 0 and 1, including 0 and 1. And the main idea is that these vectors span a much lower subspace in RL than L. Okay, so it's effectively a lower dimensional algebraic structure. That is the main idea. So the point is that there are k vectors in R to the L, and such that these mu a's can be represented extremely well in this subspace, phi 1 to phi k. How well? Exponentially good. So e to the minus k divided by log L. So up to logarithmic in the length, in the history length, I can represent any mu a extremely well. So, by the way, why is that good? Well, if I can represent it, I can learn it more efficiently, right? So I'll say how to do that. But it is the representation. This is not a full dimensional structure that I need to learn. How do we arrive to this conclusion? So we can create a matrix which is the outer product of all mu A transpose vectors, and it's this, and integrate from 0 to 1, I'm taking here a uniform measure. There is a priori no reason to take a uniform measure, but nevertheless, we do it. And these vectors are going to be the top k eigenvectors of this matrix that I constructed. So this matrix, again, is the integral from 0 to 1 of all these van der Monde vectors transposed with themselves. It looks like this. And this is a constant matrix. It's not, I can just compute the integral. So it's not data dependent. It's not eigenvalue dependent. It's made on nothing. Okay, so it's just a constant matrix. And taking the largest k eigenvectors of this matrix will have the property that I discussed. Why is that? So it so happens this is a Hankel matrix. It's also a Hilbert matrix. It's a special matrix. And what's special about it is this fact here that was proved by Beckerman and Townsend in 2016. The interesting feature of this matrix is that its spectrum decays exponentially fast. So if you look at the 25th eigenvector, it's going to be something like e to the minus 25. Okay? It's going to be extremely small. And this is great because it means that for any alpha or A, I can project it onto the top k eigenvectors of this space, and only e to the minus 25 mass remains everywhere else. And this is true for any A. It's not true for absolutely any A. So, in other words, I can write, remember that I wrote the output of a linear dynamical system as an inner product between this mu A vector and my inputs. Well, I can plug in any basis in the middle, just the identity, right? I can do a basis transform, and the basis I'm going to choose is one that represents the mu alpha vectors so well. So if I use the phi basis coming from this special matrix, then I know that I need only k parameters, and the rest are going to be extremely small for all A. Okay, if there is a question, maybe now it's a good time. Yeah.
This exponential decay will also occur if A is a vector in its spectral radius 1.
Sorry, I didn't hear.
Is this true only for this scalar A, or suppose if A is a matrix and its spectral radius is close to 1?
Uh-huh.
In that case also, will you see this like exponential decay?
Okay, good question. The question is, how do I generalize from the scalar to the matrix? This is what I showed is only true for scalars. The way I move to matrices is by diagonalization and then learning each component separately. So I can learn a transform matrix and then each eigenvector separately. Okay, so that's the way to do it. So it's actually a straightforward kind of extension. Yeah, Sarah.
I see how this lets you consider really long context length. Like effectively, you're considering really long.
Absolutely, yes.
But if A equals 1,
Yeah.
it still seems...
A equal 1. This is true for A equal 1. I mean, yeah, so it's true for all A. The theorem is true for all A.
I believe the theorem is true, but
Yeah.
somehow if you only look even exponentially L back in the past, isn't that still a problem? Or I guess it's because you're predicting on a finite horizon.
Well, the filter need to be of length of your input. So you do need to, the point you're raising is actually important. When you do online learning, let's say you don't know t in advance. Then you need to keep on increasing.
Yeah.
Now, there is a way, this is standard in online learning, it's called the doubling trick. You can kind of recompute, double this length and use it. It's going to be, I didn't want to put that, it's a bit of a mess. But it's not, there is no rocket science in extending it to any t. A. B, what happens in practice, we have a fixed context length. So in Gemini, in ChatGPT, in all of these LLMs, we have something like 32K, or depending on the model, there is a few thousands of contexts that we use. Then we're going to apply the filter only to this fixed length. We don't need to increase them. Okay? But the point is that it can be arbitrarily close to 1 over the context length. It doesn't depend on that. Yes?
I'm going to come back to my delay question.
Yeah.
Especially when you start to go to a higher dimension. One of the problems with the Hankel parametrization is that you never know whether or not CB is singular or CA to the KB is singular, and that's very much a property of the input-output lag, right? So that also, I think, then means that structurally, you might have to make some assumptions about your Hankel parametrization in order to go forward. Is that an issue?
No. So I'm not doing any Hankel parameterization.
No, but you're
I'm not
using
doing-
CB, CAB, and all that, right?
Okay, again. So, in contrast to classical theory of control, where we try to learn the parameters, I'm not trying to learn the parameters. I'm doing something else. I'm saying there might be parameters. Maybe this whole method is not going to be totally wrong. Could be off. If my signal didn't come from a linear dynamical system. But if it did, I'm doing convex relaxation. So think of like the analogy will be the lasso predictor. Learning the sparse representation is very hard, but we can learn a larger class of things that make it easier. And a similar thing is going on here. It's a convex relaxation. It doesn't capture exactly the linear dynamical system. It's a bigger class of predictors, and that's why it's capable of doing it. Okay? So I'm over-parameterizing, but still capable of, in terms of expressive power, capturing these signals from linear dynamical systems.
And your decomposition does not depend on that.
No. Yeah. Okay, thank you. Yeah. Maybe I see there is interest, but let me just do a bit more, and then I take more questions, okay? Okay, so, good. So this is, so the signal, if it came from a linear dynamical system, it can be, my point was it can be represented by only very few, something like 20, you know, after 20 we're good, 24. Then of these components multiplied by these fixed featurization. What are these M's? They're the inner products between the mu alpha and my filters. I don't know mu alpha. It has to work for every mu alpha, right? So these are parameters I need to learn. These M parameters I need to learn, but that's the only parameters I need to learn. Everything else is fixed. These filters are eigenvectors of the Hankel matrix, which is constant. It's not some learned. It's constant matrix, 1, 1/2, 1/2. You know, I can write it out, can pre-compute it, and then use these vectors to filter the input to get these kind of components here. And then these are the only parameters I need to learn that are data dependent. So this gives the following kind of method. I have these K filters. They look like this, by the way, if you try to plot them. They have this nice, first of all, they decay. They have this nice sinusoidal kind of structure, but they're very different from Fourier. The reason they are different from Fourier, because in Fourier basis, I have the same, all the eigenvalues are the same. Here we have exponential decay, right? So it's very, very different. But it looks like a spectral, beautiful filter. I can pre-compute them, and for an input sequence, I can take the convolution with these filters and then learn only the coefficients. This is depicted here. So I have my input signal. That's how it gives rise to an algorithm. I have my input signal. I convolve with these filters, or if it's only one time step, I take the inner product. This gives me the featurization. There's the learned parameters, and then I add them up to get the output. Okay. So to make one prediction, if I have K filters, it takes me KL time. If I'm doing it over a sequence of length L, I can use the fast Fourier transform. I can do convolutions. It will be L log L. So this gets rid of the quadratic running time bottleneck of the transformer. And the theorem says that it can represent any linear dynamical system with exponential precision, the exponent being dependent on logarithmic in the time horizon and the number of filters, but independent of the decay. System cannot decay, still fine. Okay. Good. So I have talked about symmetric A. The reason I talked about symmetric A or positive semi-definite A because I assume these A's are numbers between 0 and 1, right? If I have a general matrix, that is not true. If it's a symmetric matrix, the values can be negative, for example. What if I have negative eigenvalues? Okay, so there is a simple trick you can do, which, for example, you can take this mu alpha vector. What happens for a negative A? Every odd term here is multiplied by -1. That's all that happens here, right? So I can take my input and just change it to have alternate signs, or alternatively double the number of filters, where I multiply every column, odd column, by -1. So now I can have all numbers between -1 and 1. That's one way to do it. Then I can generalize to asymmetric matrices. That this is much harder now because I need to learn the phase of the complex number, and this is a hard problem. This is not a practical method, but still I think interesting. So the generalizing to asymmetric is much less practical. Okay. Now I guess, yeah, if you want to, if there was a question about any of the technical material, I'm happy to take. Otherwise, I will move to the next part. Okay. Any questions about the technical? Or there was some question I remember before. We're good? Oh, yeah.
You assume that the vector is spanning subspace of infinity, right? When delta goes to 0, L must goes to infinity, right?
No, that is not correct. So L is a fixed parameter, and delta can be 0 or not 0, and this is independent. So the linear algebraic property of the decay of the eigenvalues is absolutely correct, and it's independent of delta.
But you wanted to prove when the maximum, when the spectral radius of A is less than 1 minus delta, and you were interested in the case when you can go infinitely in the past when delta goes to 0.
Correct.
And further on, you assume that the vector is spanning a subspace of infinity in the past. You assume that the context is of length L, right?
No, okay, first part is correct, second part is incorrect. I'm going to stop now and move to the rest of the talk. I don't assume that it spans, okay, so it doesn't span. I mean, this is a full dimensional vector. In fact, the Hankel matrix is full dimensional, so, but it's nearly spans. So what happens when you take k eigenvectors, it has a very low residual on the rest of the mass. And this is true for any L. L going to infinity is fine too. The dependence on L comes logarithmically into our approximation. But how close the delta is to 0 doesn't come at all into this approximation. That's kind of the point of this technique. Okay, let me move on to some experiments. And I'll start with some synthetic experiments. This is Oviedo et al. They experiment with a linear dynamical system. And their method, so this is a very simple one. I took a linear dynamical system from their neural architecture. The diagonal is very close to 1 here. This is very close to a marginally stable system. And the point is, so this SRU, spectral recurrent unit, converges extremely fast to the correct prediction as opposed to their technique. And another thing, this is something that kind of impressed applied people. So their neural architectures requires a ton of tuning. What I told you, you can just code up. We have the code online. You can take these filters, code them up, immediately it works. Okay, so this is extremely, extremely robust, and there is no hyperparameters to tune, and none of that. So as opposed to previous RNNs that require a lot of initialization and tuning the optimization and so on. So this is, I think, an important aspect. And the reason that it is so, because it's a convex method. Convex methods are robust. You don't need to tune things so much. You know that the only local minimum is global minimum and so on. Okay, how can we create a neural architecture with this technique? And now we're just using previous suggestions by Gu et al. And Chris Ray group and Oviedo et al. And so on. So the way to do it is to take the inputs, apply the spectral transform, apply this spectral learning procedure that I described, and then apply some either nonlinearity or even forgo the nonlinearity. This will be one layer of the architecture, and you can repeat it many, many times as you want. So this is the way to move from the convex optimization building block. Again, the hope is that it can learn much longer memories because of the theoretical properties, and embed it in a neural architecture and then repeat. We tested it on a benchmark called long-range arena. Long-range arena is a benchmark for testing, as it says, long-range dependencies in the data. So here is an example of a problem that is in this long-range arena. You see this image, and you need to decide whether this dot connects to this dot here. In this picture, it does connect. But the way you feed the data into the neural net is a few pixels every time. So the machine has to remember the entire picture somehow in memory to figure out if it connects to it or not. That's a challenging task involving memory. So this is one type of task in long-range arena. There are several such things. And what people have observed, this is not my table. This is a table from a paper of Tridao and others, where they introduce Mamba. This is one type of neural architecture based on linear dynamical systems. And they show that transformers behave extremely poorly on these kind of tasks. And the reason is exactly the memory ability of certain types of linear dynamical systems. So their architecture S4 does, outperforms all previous transformer models by a significant amount. And however, I want to remark that their method is very unstable. So what this plot shows is that you need there are all these tricks you need to apply. So you need to apply some ring initialization and kind of massage the optimizer to work extremely well. This is a highly non-convex architecture. And if you tune everything just right, you will get the top-notch performance on long-range arena. If we apply our building block, and again, it has a convex component, so you can expect it to be much more robust. That is the method. We just basically apply regression, right? Linear regression on few parameters, 24 parameters, and maybe you do it in several layers with some nonlinearity in between. So we initialize it to 0, actually, which is so this was the applied people I talked to were most impressed about that aspect of it. You don't need to tune things very well, and already it does out of the box comparable to Mamba and the other types of architectures, even though this doesn't beat them yet, but it's very comparable and without any tricks and any tunings, and it's very simple to implement. Now, we add another component. So, yeah, question?
Did you compare it to any transformer type?
Yeah, so as I said, good question. So this type of LRU transformer behave horribly. This was shown by a previous paper, the Mamba paper, okay? Yeah, so they showed already that this S4, the state space models, are much better on long-range arena than transformers. Okay, back to the addition. So I would like to capture asymmetric dynamical systems. And this is hard using the spectral filtering technique, and this goes back to Amirali's question. What can we do? We can use past observation in an autoregressive learning tool. So this captures, for example, it is known that the convex relaxation of the Kalman filter is to take past hidden dimension many terms from your observation and apply linear regression on top of that. Now, that of course is very expensive. Especially imagine in neural architecture, you need to compute one feed forward, then see the observation, then use it in the next feed forward, and so on. So it's pretty inefficient, and yet it is pretty powerful. So what we do, we add a few of these autoregressive terms to our machine. So we call this autoregressive spectral transform unit, and what it does, it takes the previous machine that I described, basically spectral filtering, do the constant filtering, learn coefficient on top of it. To that, so this learns one part of the signal, and then you can imagine taking another part, another component, which is a few autoregressive components from the previous predictions. How many few? So what we find is that, few, 2 to 30 is enough to get the results that I will show. So we kind of augment this technique. I don't see it as a complete zero-shot solution, but you need to augment it with some more representative power, and that is the autoregressive component. And now this augmented machine can essentially outperform most of these benchmarks in the long-range arena suit. But still much more robust and much more stable than other architecture. Okay, so this is now work that our students, Isabel and Windsor and Evan, have been doing. This is, you're all a control audience, you know what this is, right? These are all the animals in Mujoko. And we use here some policy which was trained, base policy, trained on PUPIO or one of the standard things there. And the goal was, okay, this prediction algorithm that I described is based on linear dynamical system, which is captures a lot of physical phenomena in reality. So you would expect the sequence prediction to actually work best for physics types of problems, right? So they basically collected a lot of data, and this data is state and next state, or state control next state, that kind of data. And what they tested is, how can we predict the next state given the past states? And the hope is that we can do much better. And I should remark, this is preliminary, still being tested and verified, that in some type of architecture, it does much, much better than transformer. And you can see the comparison here. This is the walker and the cheetah and the ant and so on. It's kind of consistent across the different animals of Mujoko that you can train extremely faster than transformer. Okay? This is valid. Some of these are validation, some of these are trainer. It's pretty consistent. I find this also to be very impressive. This is another experiment they conducted. So in this experiment, they took the Mujoko image, so not having access to the hidden state of the robot, and applied image to vec, standard image to vec, that is found in one of these software packages out there. And you can get a vector representation. And what we like to predict is the next image from the past images. So this is purely image prediction. And again, the spectral transformer performs significantly better than a transformer architecture. I should remark, we have the same number of parameters, or transformer even has more parameters, and the same type of tuning has been done. But again, this is still preliminary and being tested, so I will caveat this. This is not published yet. Good. So, yeah, so let me conclude, and I have maybe time for questions. I talked about spectral sequence-to-sequence prediction, how we can provably learn a marginal stable linear dynamical system. We can stack it to create a deep neural network architecture. It's hyperparameter robust. This is, I think, extremely important. The reason it is robust is because it's convex. Basically, we have a convex machinery hiding underneath. I showed some experimentation. We're exploring hybrid architectures. I really believe that this is the correct answer, should be somewhere in between. Some kind of attention and some kind of spectral featureization and some hybrid. This is also being explored by other teams, Tridao and others. And if you want to learn more about it, and generally about online control, which I think is a very interesting paradigm, I wrote here a book which you can find on arXiv. And thank you for your attention.